Alright, ladies and gentlemen, class recording has started. It won't be nearly as exciting as the pre-class recording discussion, but, well, I guess we'll wait and see, I guess. So. Alright, yesterday we talked about stellar evolution and what process a star goes through, from how it starts to eventually how it's going to end. We didn't get to the ending part yet, we'll do that today. But how it starts pretty much gets summed up with this picture right here. Right? You guys don't have this picture, but it's on the first page of your outline for this section. Right? A star starts as a nebula, a big collection of gases and dust and little particles and stuff like that. And then the thing ultimately responsible for starting the star is what? Gravity, right? Gravity starts pulling it all together. And as it pulls it all together, right, the more mass you have, the more gravity you have, starts pulling more things in, and eventually we start getting the conditions correct in the middle here for fusion to start. And we said that we have to have a balance of two things. What are the two things that have to balance in order for us to get a star? Nick, go ahead.
Gravity and the outward force from fusion.
Gravity pulling stuff together, right? And that outward force from fusion pushing it all apart. Basically, the heat or the energy that's released during fusion, right? Okay. And if those two things balance, we get ourselves a star. And specifically a main sequence star on the HR diagram. So there's our HR diagram, right? And we said that the one key factor that determines where a star ends up on the main sequence is what? Mark, good.
It's mass.
It's mass, right? Mark, give me a summary real quick of how the mass determines, or not how it determines, but where mass dictates it ends up on this main sequence.
Well, the larger the mass it is, the closer to the top left corner it's going to be.
Okay.
The smaller the mass, the closer to the bottom right.
So bigger mass is up here, smaller mass is down here, right? So our bigger mass stars, what kind of star, or our bigger mass nebulas, what kind of stars do they turn into? What kind of characteristics are these stars up here going to have? Eris? They're going to be hot. What else? They're going to be blue, and they're going to be, yes, one more thing I'm looking for. Bright, right? They're going to be hot, they're going to be blue, they're going to be big, they're going to be bright. But the trade-off being, right? What's the trade-off being? They don't live that long, relatively speaking, right? We're still talking about tens and thousands of years, right? Or tens and hundreds of thousands of years, but relatively speaking, that's not that long, okay? All right, down here, right? Pretty much flip it all around. So stars down here, what's their deal? What's their characteristics of these stars?
They're small.
They're small,
Not that bright.
not that bright,
They're relatively cold.
relatively cold,
And they live for a long time.
live for a long time. Here we're talking about like millions of years, right? The mass of the nebula that starts this star pretty much dictates where it ends up. Okay? Good there. All right. So now let's talk about these stars. Like, how do we get up here? How do we get down here? And the answer to that is, well, you got to run through the course of what being a star means. So, let's go. So we got this, right? And we end up on the main sequence. And we said that, Nick, two factors really, as long as two factors are good, star will end up or stay on the main sequence. And what are those two factors? Gravity and fusion, right? Gravity pulling it inward, the heat and the energy released from fusion causing it to expand and pushing it outward. As long as those two factors stay in balance, star's good to go. Okay? Which one's going to stop first?
Fusion.
Fusion, right? Gravity's gravity. As long as you have mass, you have gravity. That doesn't stop. So fusion is really what dictates what happens next. So, stars will remain stable as long as the outward push produced by the energy of fusion balances the inward pull of gravity, right? And we just discussed that. So, what happens next? As long as those two are in balance, we're on the main sequence. Regardless of how big of a star we have, the same thing happens at the beginning of the end. Okay? First thing that happens, fusion slows. Why? Because it runs out of stuff to fuse together. Mainly what? What do we fuse? In fusion, what happens? We turn
Hydrogen into helium.
Hydrogen into helium, basically, right? So we start running out of hydrogen, and that percentage of hydrogen to helium starts favoring towards helium. So the fusion slows and the outward push decreases. Gravity takes over and begins to shrink the star initially. That's what happens first. Now you may say, well, wait a second. These stars here, our red giants and our red supergiants, they're bigger than the original star. So that doesn't make sense. True. But once gravity becomes stronger than that outward push from fusion, right? Now the shrinking raises the pressure and the temperature inside the star. And now, if there's higher temperature and pressure, we can do fusion. But it's not just in the core of the star. Now, fusion starts happening outside the core because the conditions become suitable for that to happen. Now you've got fusion not just going on in the middle, but on the outside edge and all kinds of in different places, and now it sort of kicks back into gear, right? Not to be morbid, right? But sometimes you'll hear stories of people who are sick for like a really long time. They have like a debilitating disease or something, and they've been in the hospital for a couple months, and then all of a sudden, one day, they're like themselves again. Like, they're just energetic, and they're talking, and if they have like, you know, maybe if my grandma had Alzheimer's, so she was kind of like this, like, but like one day she was just with it. Like, she remembered everybody and knew everybody, and then like, that's sort of like, when that happens, it's almost like an indication, like, okay, this is the end, because something happens and it like kicks them into gear or whatever, and then after that, it's just goes downhill. It happened with my grandma, so I can tell a personal experience, right? But that's sort of the thing that happens here with the stars, that it kind of the fusion slows, gravity pulls it together, and then that sort of kicks fusion back into gear, but in a little bit higher gear than it was before. And then that causes the star to expand into what we call a red giant or a red supergiant. Same idea, just on a bigger scale. Okay? So that's the beginning of the end, right? Fusion slows down, gravity takes over, scrunches it together, but by gravity scrunching it together, now the conditions for fusion don't exist only in the core of the star, but they exist in other places, and that causes fusion to sort of kick back up, and now the outward push gets bigger, and it swells up. Right? And this happens to every kind of star, big and small, regardless of their size. Okay? What happens after that is really determined by the size of the star. Right? So, let's talk about our star. Right? The core continues to shrink and gets hotter. Helium fusion starts. So when we turn hydrogen into helium, we go from one proton to 2 protons, right? But now we start taking 2 and 2 and make 4. Or we start taking 2 and 1 and make 3, right? So now we're getting other elements than just hydrogen and helium. But this only happens at the end of a star's life. And not all of the helium that got made throughout its life turns into other elements. That's why if you look at the percentage of elements that exist in the universe, hydrogen and helium are by far the highest percentage of elements because most stars are doing their thing. The other elements, lithium on up, exist at a much lower percentage. Why? Because the conditions don't exist very often where we can fuse those bigger elements together to make bigger ones, right? Because the conditions don't exist where we can fuse 2 and 2 together and make 4. Or where we can fuse 4 and 4 together and make 8. Right? It's even harder to do that. So if you look at the percentage of elements out there in the universe, not here on Earth, but in the universe, hydrogen and helium are by far the biggest ones, by far the highest percentage. Okay? So We start doing helium fusion, heavier elements get created. But if you have heavier elements, getting those heavier ones to fuse together into more stuff becomes even harder. And eventually, the conditions just aren't there anymore, and fusion is going to stop. Okay? Once the fuel of the star starts to run out and fusion slows down, that star will enter its final stages. And those final stages look like this. Okay? Just like the mass determines what kind of star it's going to be, the mass will also determine what's going to happen to it at the end. All right? So let's first talk about what happens to low to medium mass stars. Okay? They swell into red giants, and that's going to happen to our star. This top row here, that's pretty much what happens. This is going to be the route our star takes, okay? Our sun. Right? First, it swells into a red giant. And when we say it swells, this picture doesn't do it justice, okay, as far as how much it swells. When it gets to the end, our sun is going to expand to the point that it's going to gobble up Mercury and gobble up Venus and gobble up Earth and gobble up Mars. That's how big it's going to get, right? Not all the way out to Jupiter, but in that spot, okay? But then after that, low to medium mass stars will remain as giants until their hydrogen and helium completely runs out and fusion stops. Eventually, the conditions just aren't going to be there for fusion to continue, right? The stuff that it made is too big, it's not hot enough, right? There's not enough pressure, it's not enough gravity, it's spread out. Fusion's just going to stop. And now I know this sounds kind of counterintuitive to what you think might happen, okay? But when fusion stops, gravity takes over and starts pulling the middle back together. But because it has swelled outward, that stuff being spread out over such a big area prevents gravity from bringing it all back together. So it swells and swells and swells and swells and swells, fusion stops, and then it just kind of goes. That's my scientific description of what happens at the end. So it ends up surrounded by this cloud of gas, and it's glowing because it's still pretty hot because it was a star not too long ago, and we call it a planetary nebula. So that planetary nebula is just the stuff that's around it, right? That is the leftover part of the star. Okay? Just finish this. Okay. You okay? So then, gravity does pull a little bit. I know there's stuff to fill in here. Let me finish this, and then we can fill it in as we go along. So, okay. All right. After that, the middle, what used to be the core of the star, is still very hot. But because it's just a small percentage of what the star used to be, right, it's small. So it's hot and small, and that's what we consider a white dwarf. It's very hot, so it's in that temperature range of white, because it used to be the core of a star, but now it's just kind of glowing. But it glows because it's still hot, but it's not doing fusion. So eventually, what's going to happen to it? If it's not creating energy from mass, eventually it's going to do what?
It's going to cool off.
It's going to cool off. And as it cools off, it's not as bright anymore. Right? Just like this is like the glowing coals that are left over after a campfire. Even though the fire may be out, those coals are still hot enough that they glow a little bit, right? And that's really what it is. But just like a campfire, eventually those coals cool off, and we end up with something called a black dwarf. Why? Because it's still a big thing of mass, right? It's still a big collection of mass, but it just doesn't glow anymore. It doesn't give off light, right? So it's kind of just a big collection of mass. Right? So let's go through the bottom there, right? How long do stars continue on as giants? As long as they're still doing what? Making hydrogen and helium, we call that fusion, right? As long as they continue fusion, they'll continue on as giants. Okay? But where does the material of planetary nebula come from? So the planetary nebula is what? The remainder of the star, right? It used to be part of the star, but now it's spread out over a big area because of that expansion that happened, turning it from a main sequence star into a red giant. Why does the white dwarf still give off energy even though it doesn't do fusion anymore? Still hot, right? It used to be the core of a star. It's pretty hot still. Okay? But that star becomes a black dwarf when what? Eventually it cools off, right? If it's not doing fusion anymore, it's just going to cool off eventually and kind of just turn into a collection of solid mass. All right, we okay there? Okay. Whereas my description of this size star and its eventual demise is, right? The other ones, though, way more exciting. Yeah, so let's talk about the other ones, all right? Yeah, much better, all right? So if I had to give this one a description, it would be like in the old Batman cartoons. There's like a big, like, you know, pow. That's where we're going right here. So, okay. All right, so first, it still does the swelling and turns into a, not just a red giant, but a red supergiant, right? If you look back at your HR diagram, okay, so flip back over 2 pages and look at your HR diagram. Classification of red supergiants. What would you tell me about red supergiants? Nick? They're very bright, but they're not that hot. And the reason why they can be bright but not that hot is because what? They're huge, okay? Hence the name, supergiant. You don't just throw around supergiant lightly, all right? So, yes, Sid?
Do you think once a star starts expanding, it can like swallow up other stars?
If it's big enough, sure, yeah. And that actually sort of helps its case almost. Because remember we said this happens because fusion starts kicking up in areas outside of the core. So if it's big enough that it actually starts swallowing other stars, that might actually contribute to being a red supergiant. Because if it's got more gravity, which it will if it gobbles up more mass, right, then it can actually help its cause and make it even bigger, right? But yeah, and I mean, the likelihood of it, stars are really far apart. Well, at least stars around us are. If you get towards the center of the galaxy, which we'll see in a little bit, sure, I think it's possible, although I don't know if it's ever happened or not, so. All right, so high mass stars turn into supergiants. Supergiants have sections. Remember we said that the thing that causes it to become a giant or a supergiant is that fusion starts occurring outside of the core, and that those conditions exist where it can start fusing helium into other things. Here, in supergiants, conditions sufficient to produce heavier elements up to iron. Iron has an atomic number of, Jeremy, you have your periodic table out. Do you see where iron is? 26, right? So the conditions in a supergiant are hot enough, pressure's high enough, that it can fuse up to 26 protons together. Okay? That's pretty, pretty hot, pretty impressive, right? But it still only gets us to 26. Okay? Naturally in the universe, we find elements up to 92. So there's got to be something else that takes it even farther. And that's something else right there, baby, yeah. Right? So, fusion stops. Because it's a huge star, gravity starts pulling it back together, especially the middle, right? We talked about in the lower mass star, the rest of it just sort of becomes, right, a planetary nebula and nothing happens. But because in the bigger mass star, there's so much gravity, it pulls that core together, makes the pressure so great and the temperature so great that it just can't hold it together anymore, and boom, we have what we call a huge explosion called a supernova. In that supernova, the conditions, at least for a very short time, are so great that it can fuse iron into higher elements. And in supernovas, that's where we have the conditions that are sufficient for us to produce all those elements from 26 up to 92 that we see occurring naturally. So these conditions that exist in the supernova, that's where we get those elements. Not very many stars go supernova, meaning that the percentage of those elements is much smaller than the percentage of other elements. If you look at the percentage of something higher, like, just for the sake of argument, uranium is 92, right? The percentage of uranium that exists in the universe much smaller than the percentage of, say, like nitrogen or oxygen, which are 7 and 8, right? Because the conditions just don't exist that often where it happens. Okay? All right, after that, couple of things, weird things can happen. Okay. Our quote-unquote smaller big stars. I know that's kind of oxymoronic, but you know, we're talking here, like, if I'm not mistaken, stars that are in the range of 20 to like 50 masses of our sun. And that's a round ballpark figure. Okay. Turn into something that are called neutron stars. Neutron stars are very, very dense, and the conditions are appropriate that it can take individual protons and individual electrons and smash them together to form neutrons. Hence the name neutron star. But then, our biggest big stars, right? They go black hole. Right? Our bigger big stars turn into what we call black holes. What happens inside the black hole? Does it make neutrons? Does it make what? We don't know. We don't know what goes on inside a black hole because the gravitational pull is so strong that nothing gets out of it, not even light. So going back to our discussion from the previous section, previous units, do we see a black hole? No, right? How do we know it's there?
Because there's no light there.
There's no light there. What else are we going to see happening around it? Because it has a super high amount of what? What sucks things into it? Gravity, right? It has a huge amount of gravity. So we start seeing things for lack of a better term, gravitating towards this one spot where we don't see anything. And so we put 2 and 2 together and go, oh, must be a lot of gravity there, right? But we don't see it. What happens when we go into a black hole? Don't know. Because can't see what happens when we go into a black hole. Weird stuff starts happening on the way to the black hole, but once it actually enters the black hole, we don't know what happens to things. Okay? This is a discussion for another day. It's a really interesting discussion, but we don't have time to get into it a whole lot. Sorry. So, Suzanne, go ahead.
There's this Doctor Who episode. It's like the Impossible Planet or something.
Okay.
Because they have like they're on this like rock and there's a black hole above them, but this not moving, or they're not being sucked into it.
Weird. That is so, yeah, there's all kinds of hypotheses about what might happen when you go into a black hole and what a black hole is. Some people think it's a big funnel that leads out of our universe and into another universe, and there's all kinds of hypotheses. But the answer at this point is we don't know because we can't see what happens. Right? We can't. Connor, go ahead.
Has anyone ever gone to the
too far away for us. Like, yeah, there's nothing, there's no black hole that's close enough for anybody to get to. Right? Second, even if somebody did go into one, they couldn't tell us what happened for two reasons. One, they would never come out of it. And two, the gravitational pull is so strong that it sucks up light and other kinds of electromagnetic radiation. We communicate in space through radio waves, which are low energy electromagnetic radiation. Radio waves don't come out of a black hole. So it's not like we could send somebody in and say, hey, tell us what you see. Because the signal that they would use to tell us what they see doesn't get out. All right? So yeah, go ahead.
Like, what do you think happens to when black hole sucks and stuff? What do you think happens when the black hole like closes and stuff? What happens to the stuff in it? That's a question I'm thinking.
That's a big don't know.
Yeah.
Like, I mean, here, a neutron star has gravity that's strong enough to smash protons and electrons together to make a neutron. But a black hole has stronger gravity than that. So what happens when stuff goes into it? Now, one of the things that we sort of see, this is a weird one, we'll go with this, but one of the things that we see start happening, right? Gravity depends on two things. It depends on mass and it depends on distance. So technically, as you stand here on Earth, your feet feel more gravity than your head does, because your feet are closer to the Earth than your head is, technically. But the difference is so small that it's not perceivable to us. Okay? But as you get closer and closer and closer to a black hole, where the gravity is stronger and stronger and stronger, if you were going feet first into a black hole, your feet would feel more gravity than your head does, but because the gravity is so strong, it's a noticeable difference. When certain things feel more force than other things, what happens to them? If your feet are getting pulled on more than your head is getting pulled on, your feet are going to start moving closer to the black hole faster than your head's going to start moving closer to the black hole. And you get yourself stretched out, right? Not lying about this, right? I did not make this up, okay? The term that we refer to this as is spaghettification. Not joking on that, all right? That's a real term. Okay? So yeah, that starts happening until it like splits you in half.
Oh.
But then, now there's two of you, right? Okay, you got your torso and your legs. But guess what starts happening to your torso and your legs? They start spaghettifying, okay? And then they split into four. And then guess what starts happening there? Then then you get eight. And then eventually you get to the point of the black hole where we can't see anything else. And then what happens after that? We don't know. So yeah, it's a great discussion. And if you know anybody who's in physics, we did this a couple weeks ago, and there's a lot of like contradictory things that if you talk about black holes, you start realizing that a lot of the things that we thought we knew, we didn't know, and we have to reevaluate everything that we thought we knew in light of contradictory evidence. All right? But like I said, a story for another day. So, all right. So that's our stellar evolution, what happens there. Okay? Let me give you this and this. Okay. All right. Here is your objective sheet for this unit on nuclear reaction, stellar evolution, and origins and fate of the universe. In that section, there are two objectives that relate to galaxies. That is terrible, so let me do that again. All right, so number 12 and number 13. Alright, so number 12 on your list of objectives for this section says describe gravity formation. That basically can be pretty much summed up in one word, and that is gravity. Alright? 13, compare and contrast the different types of galaxies based on their size, number of stars, and the relative age of the stars. What you'll find out is that there are 3 types of galaxies. 2 types, and then sort of a miscellaneous. So that's where we are. The section on galaxies starts off on page 674, which is in chapter 20. Okay. So those are your 2 objectives that you need to know. So page 674 in chapter 20. Those are the 2 objectives that you need to know about galaxies. You have about 10 minutes right now. Hopefully you can get that taken care of. Okay. If not, finish that up for homework this evening. Okay. You need to be familiar with these things. Will there be a lot of questions on the test? Maybe not a lot, seeing as how I didn't really lecture on it, but there will be a couple of questions about galaxy formation, right, and different types of galaxies. So that will show up on your test. Not a lot, but it will be there. Okay. Tomorrow we will talk about beginning of the universe, possible end of the universe, how it all started, how we think it might end. Good philosophical discussion there. So that's where we're headed tomorrow.